Hi everyone! In today's lesson we will be studying mathematical proof by induction, which is a topic in the IB Math AA high level. Now, to prove statements by mathematical induction, you follow these three steps. First, for any question, for any statement, we prove the statement true for the first value, which is usually 1. It's not always 1, but most of the times it's 1. It could be 0, could be 2, anything, but mostly it's 1. The second step, which is the inductive hypothesis here, we assume the statement is true when n equals k. And thus, the third and the last step, which is the most important one, we use the assumption in step 2 to prove the statement is true when n equals k plus 1. We will clarify everything now with this example. Here we need to prove this statement by induction. Here we have the factorial notation. Remember, we made a video about it. Like here we have 3 factorial. Previously, like we made a video, we said that, for example, 5 factorial is 5 times 4 times 3 times 2 times 1. We start from the number, then up to 1. Here we need to prove it for values of n bigger than or equal to 1. So first, we will do the first step. We'll prove it true when n equals 1. We'll prove here both sides true when n equals 1. So first here, this is the left side. Here we have the left side. When n equals 1, here when n equals 1, here 2, here 3, and so on. When n equals 1, we take only the first term, which is 1 multiplied by 1 factor, and that will be 1. Now let's do the right side separately. Replace also here n by 1. Here you'll have 1 plus 1 factorial minus 1. This will be 2 factorial, which is 2, and then 2 minus 1 will be 1. Notice that the left side and the right side are equal. Since they are equal, then the statement holds true for n equals 1. Now the next step will be the inductive step, where here we assume the statement to be true. We don't prove it, we just assume it to be true when n equals k. But it's very important to write it down. This will help you a lot in the next step. So here we assume the statement true for n equals k. You write down the same statement, but instead of n, you put k. Notice that here n times n factor will be k times k factor, and here n plus 1 will be k plus 1. This is true, assumed to be true, so you can use it in the next step. The third and the most important one here, the most important step, which is the inductive step. We use the assumption in step 2 to prove it's true for n equals k plus 1. So now we will prove this statement true for n equals k plus 1. So here we'll prove it true for n equals k plus 1. Now it's very important to write down the statement that you are proving for n equals k plus 1. So let's say that this is the aim that we are proving. We write it down, but we replace n by k plus 1. See here, it will be from 1 to n, or here it will be from 1 up to k plus 1. Notice that here the n and the n factorial are k plus 1 and k plus 1 factorial. Here also we replace this n by k plus 1. And you have here another one. It will be k plus 2 factorial minus 1. Keep in mind, we still need to prove this true. So now here we'll see the steps. Here we use our algebraic skills, our logic, or any knowledge we have to prove what we need. We will prove this statement here for n equals k plus 1. So we will start with the left hand side. We work on it till it becomes the right side. Let's start with this left hand side. Notice that the left hand side as it is, 1 times 1 factorial up to k plus 1 times k plus 1 factorial. But here I wrote these terms in purple for a purpose, just from 1 to k factorial. Because don't forget that from 1 factorial here up to this k factorial, this is what we assumed to be equal to k plus 1 factorial minus 1. This statement here is assumed to be true, so we can use it. That's why I replaced all of these in purple by what's equal to them, which is k plus 1 factorial minus 1, as you see down in the next step. But these k plus 1 times k plus 1 factorial, I kept them here as they are. Now, why did we write down this aim? I told you it will help you. See now here. So far we are in this step. I need to work on it and manipulate it till it becomes the right side I'm trying to reach here. So first, I moved this -1 to the end of the statement, because here, as you see, it's in the end. But I wrote the k plus 1 factorial here before the -1. I just switched places here. Then, notice that here we have k plus 1 factorial, and here we have k plus 1 factorial as well. That's why I factored it out as a common factor only from these two terms. But I kept the -1 as it is. So here, if you factor the k plus 1 factorial from both, here you will have 1 only for this. Notice that k plus 1 factorial times 1 will be this. Then, plus the k plus 1 you left from the other term when you factor here. So you have 1 plus k plus 1 and then minus 1 as it is. This bracket here will be simplified to k plus 2. So we have k plus 1 factorial times k plus 2 minus 1. Now here we have an important step. Notice that here, if I stop here, it's not the aim I'm proving. I need to make it like this. Here, I will remind you about something very important in factorial. You know that 5 factorial is 5 by 4 by 3 by 2 by 1. If you multiply 5 factorial by the next immediate number, let's say here it will be 6, then this will be 6 factorial. Notice that 6 factorial is 6 multiplied by 5 by 4 up to 1. Here, 6, and then the 5, 4, 3, 2, 1 are all in 5 factorial. So here, that's why when you multiply 5 factorial by the next number, you'll get 6 factorial. Same here. When you multiply k plus 1 factorial by the next number, k plus 2, it will be then k plus 2 factorial minus the same one. Notice that we reached the right side that we are proving. So equals to the right side, which means the statement is true. So the conclusion would be, since the statement is true for n equals 1 and k plus 1, then the whole statement will be true for values of n bigger than or equal to 1. So this is how we do proof by induction mainly.